Hi, I'm Sai, and my team has presented Fair Federated Learning for Skill Lesion. Our URIC ID is 16451, 16541, and let's go ahead. Coming to the overview, it's introduction, literature review, problem, dataset, methodology, result, conclusion, reference. Now, in introduction, medical imaging has come a long way, especially for things like skin lesion detection. AI models can classify lesions pretty accurately. But here's the thing, the models aren't pretty fair. They might work well for one group of people, say male patients, but then for female patients, they'll work way worse. And this is a very serious problem because bias is a very important factor to be considered. Now, let's add another layer to this. Skin lesion data is medical data. People don't want their images being sent around to different hospitals or institutions. Like who wants their data to be sent around uh, different hospitals or different institutions. So there's a privacy concern here too. So what we are trying to do is tackle both of these problems at once. We use federated learning, which basically means the data stays locally and only the model weights are sent to the global model. And on top of that, we add fairness mechanisms to make sure that the model is isn't biased towards any particular group, any particular client, or any particular client's performance as well. So the idea is high accuracy is great, but it needs to be fair accuracy for everyone. And because of this, we achieved around 97.6 accuracy and 0.976 to F1 score. Now let's go ahead for literature review presentation. Now coming to the literature review, there we have cited around 11 papers, and in these 11 papers, each one of them has its own advantage and disadvantage. Some have stable training advantages, but then they have not implemented all of the fairness metrics properly. There's three fairness metrics, which I'll be talking about them later. And some of the disadvantages would be extra training complexity, limited fairness has been applied, or limited model level fairness and stuff like that. So everything is a combined framework of the fairness metrics has never been proposed, and this is what we are doing. So the problem is here we do not have a combined fairness metric. Fairness consists of three metrics: demographic, collaboration, and performance. And there is no such implementation or a weighted aggregation strategy such that all these three have been implemented and given equal or decidable weights to each. So this is what we are trying to bring up. We are trying to uh, make a uh, make a weighted aggregation strategy, and so that the model is fair over all the aspects. Now coming to the data set that we used 15,670 lesion images from. We have used ISIC dataset, ISIC 2018, 2019, 2020, and 2024. From 2018, we took 662 positive cases. From 2019, we took 4,522 positive cases. And from 2020, we took 584 positive cases. And from 2024, we took all of the images, which were 10,000 benign images and 393 malignant cases, totaling up to 15,670 images as a whole. Now, coming to the methodology, we introduce three types of fairness into uh, into a federated aggregation strategy, and this would be three types of fairness: would be demographic fairness, collaboration fairness, performance fairness. Let's understand what each of the fairness is, and yeah. Now, coming to the demographic fairness, how this fairness mainly shows how different groups are treated by the model. So different demographic groups as in age, gender, color, and stuff like that. And we have segregated it into two the two factors, age and gender. So demographic fairness, we considered age and gender as two factors taken into consideration, and this is one part of the three fairness metric fairness weighted strategy. Second would be collaboration fairness. Now, coming to the collaboration fairness, how each client in the federated model has contributed for the performance of the global model. Now, the global model could be sometimes what happens is one client gives more contribution because of its higher accuracy than the other clients, and this should not happen. And every single client, even with its data set limitations or model limitations or local model limitations, it should be able to contribute to the global model in the same level so that it can distribute its weights properly. So we have divided it into zero point 0.4 into participation rate plus zero point 0.4 in model contribution plus zero point 0.2 into resource score. Now, performance fairness here, what this basically means is how each client performs in the local model and how their contributions are to the global model's performance. Now, and this is basically done using accuracy weights, F1 score weights, and performance weights. And all these three combined, we make a weighted aggregated strategy. Now here is a weighted aggregator strategy. Each one has a hyperparameter alpha, which gets tuned in the model training part itself, alpha, gamma, delta, or we can even set alpha, beta, gamma, delta as required, and these could basically be the weights of the particular model. Like if we set alpha more, then performance rates will get higher. If we get delta more, we can get collaboration weights higher, stuff like that. So this is fairness weights, the fairness that the model uh, gives itself. And yeah, now coming to the architectural diagram, we basically send 15,000 images and then we do some data pre-processing. And this is a global model and local model and fairness weights. We get local model weights and to the global model, and we send model and fairness weights, and we continue the training across all the flight clients equally. Yeah. Now coming to results. Results are the test accuracy comes around 97.63% and F1 score being 0.9762, and how we'll see how each client has also performed. Client 1 has 97.45 accuracy, client 2 has 96.58, client 3 has 98.64, client 4 has 97.68, client 5 has 96.98. Now coming to the equalized odds and multimodal ISIC dataset and all the other methods that are there. Using the four methods that are there, either they don't have all the metrics, or their accuracy is not high enough. Now, our proposed method has all the metrics, and our accuracy is higher, and we have tested it on two data sets, and equalized odds is also there. Equalized odds is basically like it basically is how accurate predictions are done across each model group, each demographic group, and over gender. The lower is the better, and we got 0.015 as equalized odds, which is better than all the other proposed models. Now, this is uh, an ablation study of, or an extra study of 20 rounds, and we can see that the original test loss and the test loss is the same, so we don't need to worry about the way the metrics are changing as a whole. Now, coming to the conclusion, skin lesion classification is a very research topic, but then federated learning with fairness has been very overlooked. And this model introduces demographic collaboration performance fairness, which improves its fairness as a whole, which makes it a better model than the current ones, and which could basically give a more fair outcome to the model, give a more fair answer to the model. And give more fair outputs because of the model. And in healthcare and medical applications, is very important. Coming to the references, we have used these two references. Thank you.